First of all, I would like to thank very much the organizer for this kind invitation to this stimulating and well-organized meeting. My contribution will be on a spectral property of the step-length selection strategy in a gradient method for differentiable optimization, both in the unconstrained and constrained case. In the step-length selection strategy is a widely studied topics in unconstrained optimization, but in my opinion is less investigated in the case of constrained optimization. Then I will start by recalling some well-known basic ideas on which are based the standard step-length selection rule in the unconstrained case. And then I will try to explain how, in my opinion, this step-length rule needs to be modified in order to work efficiently also in the case of constrained problem. Finally, I will consider some possible generalization of these ideas in the case of scale gradient projection methods that are, in my opinion, very important in case of imaging applications. Okay, our interest is in defining step-length updating rule for this step-length parameter, denoted by alpha k in red in this gradient projection scheme for differentiable optimization with simple constraints, where simple means that the projection onto the feasible region is not expensive. The motivation for this analysis is due to the fact that in many situations, in presence of constraints, the authors take the step-length rule defined on an unconstrained problem and then try to exploit this step-length rule also in case of constraint. But this we will see that is not always the best choice. Then the first part of the talk on the unconstrained case. And I start by recalling basic steps that in many cases are followed for designing a step-length selection rule in an unconstrained case. First of all, the rules are designed in order to try to capture some second-order information in an inexpensive way. Usually, these rules are designed in the simple unconstrained quadratic case, where the second-order information are related clearly to the spectral property of the Hessian matrix A. And then, always in an inexpensive way, this step-length rule are generalized to the case of general non-quadratic function, objective function. A good example of this way to defining step-length rule is provided by the Barzilai-Borwein rule and also by improved Barzilai-Borwein rules. In fact, the Barzilai-Borwein rule are defined by imposing to the step-length parameter this quasi-Newton property, also known as a second condition. In this way, we obtain two step-length rules that depend only on the difference between two successive iterations and two successive gradients. The rules are then inexpensive since they exploit quantities that are already available within the iteration of the scheme and are already able to work also in general non-quadratic case. In order to explain how this step-length rule may be generalized to the constraint case, it is important to understand some spectral property of this rule. And this is easy to do in the case of a spatial quadratic unconstrained case. Suppose to have this objective function. You can consider a diagonal Hessian matrix since this is not a restrictive condition. And then look at the relation between the gradient component of two successive iterations. From this equality, it is clear that it is important to exploit for the step length alpha k values that are close to the inverse of an eigenvalue. In this way, this product, alpha k times lambda I, is close to 1, and then a strong reduction of the component I of the gradient will be obtained. In particular, if you have exactly the inverse of the eigenvalue of lambda I, the correspondence component will be reduced to 0, and they will remain 0 also in the next iteration. Then the suggestion is try to exploit Steplength rule that provide good approximation of the inverse of the eigenvalue of the matrix. The Barzilai-Borwin rule that I recalled are suitable steplengths to do this, since they satisfy these inequalities. Both the rule provide values within the spectrum of the inverse of the Hessian matrix, and in particular the second rule at each iteration provide values that a value that is lower than the value produced by the first rule. Here I have reported the behavior of the step length during an iterative process with respect to the inverse of the eigenvalue denoted by this blue line. As you can see, the value of the step length are within the spectrum of the inverse of the Hessian, but the way in which these values are generated seems almost randomly way distribution of this step length. Then a possible idea to improve this step length rules consists in try to introduce some strategy to accelerate the approximation of the inverse of the eigenvalue in order to avoid this random generation of value within the spectrum. In order to design this improved rule, it is necessary to clearly understand the effect of a step with a step length close to the inverse of an eigenvalue, not only on the corresponding components of the gradient, but also in correspondence of the other gradient components. In particular, if I take the step length equal to the inverse of lambda I, then I have the strong reduction of these components. I have a reduction of all the other components with corresponding to slower eigenvalue, but I can have an increase of the gradient components with, which correspond to larger eigenvalue. This is due to the fact that this product, alpha k times lambda j, in the last case, in this case, is can be much larger than 1. So we can summarize this consideration by saying that if you use a short step close to the inverse of a large eigenvalue, then you are in the first two situations. But if you use a large step length equal to the inverse of a small eigenvalue, then you are in the first situation, but also in the third case. Okay? Then large step length is useful for reduce a gradient component, but dangerous for possible increasing in some other gradient components. Then one can try to organize the step length selection in order to perform few large steps, and only when the step length is a good approximation of the inverse of a small eigenvalue. The possibility to capture this last information, that is, when a step length is a good approximation of an inverse of an eigenvalue, can be obtained by observing that the ratio between the second and the first rule of Barzilai-Borwin provide information about how the gradient is approximating an eigenvector. Then when this ratio is close to 1, one can try to exploit the first rule that, due to its definition, will give a good approximation of the inverse of an eigenvalue. Okay, this is not easy to summarize, but the idea is try to exploit a sequence of a small value, for example, provided by the second rule, in order to reduce many components of the gradient. And then when this switching condition suggests to exploit a good approximation of the inverse of an eigenvalue, then switch to the first rule. In practice, we can summarize in formulas this consideration, and then we have a very simple strategy. These are called the alternated Barzilai-Borwin rule, and as you can see, they suggest to exploit the second rule, or the minimum of the value produced by the second rule for some iteration. Then when the switching condition suggests to exploit the other BB1 rule, you can switch to the other rule. If we try to show the behavior of this modified Barzilai-Borwin rule, this improved Barzilai-Borwin rule, on the previous example, on the previous toys problem, then we can observe that the strategy to approximate the inverse of the eigenvalue now is not random, but follows some kind of order in order to achieve a fast approximation of the eigenvalue. This seems to provide interesting saving in the number of iterations. And then we can consider this some kind of improvement of standard Barzilai-Borwin rule. We have verified this behavior also on many other quadratic randomly generated test problems, and usually we find convenient to work with the Barzilai-Borwin rule, but in this alternated way. Okay. In the quadratic case, there are many other suggestions, but only few of these suggestions can be extended to the non-quadratic case in an inexpensive way. And Barzilai-Borwin and all the rules based on the Barzilai-Borwin ideas have this important property. If I try to work in the general non-quadratic case with these strategies, I need to recall that in order to prove the convergence of the scheme, it is necessary to include a line search strategy. And in this case, the step length selection rule will give only a tentative step length. Then the line search will decide if this step length can be accepted or need to be reduced. Here I denoted a non-monotone line search, but of course we can use also a standard Armijo rule, monotone rule. Okay. The behavior of this different strategy also in the general non-quadratic case is very similar to the one that I described in the quadratic case. That is, generally, the alternated rule performs better than the use of a single Barzilai-Borwin rule. Why this behavior? Since the alternating strategy is designed on the quadratic case. A possible explanation is that the behavior of the iterative process in the general non-quadratic case with respect to the spectrum of the Hessian matrix can be described like in this simple example. That is, the Hessian matrix in the general non-quadratic case change at each iteration, of course. But after the first iteration, the Hessian matrix tends to stabilize, and then also the eigenvalue of the Hessian matrix will stabilize, and then the step length rule works as in the quadratic case, but with respect to the spectrum of the Hessian matrix at the current iteration. Okay? Given this consideration on the unconstrained case, I can go to the introduction of the strategy to adapt this rule to the presence of constraint. I will discuss the simple case of box-constrained problem. First of all, it is necessary to observe that, of course, when a gradient projection scheme is used for a constrained problem, of course, we have very different situation in comparison with the unconstrained case. The goal now is no more to reduce to zero all the gradient, of course, and in particular, the presence of the projection step make much more complicated the relation between the gradient of two successive iterations. However, there is many work in which the Barzilai borrowing are used also in this context, in this constrained context. And in particular, there are results that confirm that the alternative strategy, also in this constrained case, work better than the single use of a standard Barzilai borrowing rule. Then it seems that also in the constrained case, there is the same behavior of the unconstrained case. And then, in my opinion, it is interesting to understand why we have this situation. To do this, I recall, first of all, the detail of the gradient projection scheme in this case, just to recall that also in this case, for the convergence, it's necessary to have some kind of line search. Okay? I start my analysis by considering also in this case a simple case, quadratic case, subject to both constrained case. The main differences from a theoretical point of view between the unconstrained and the constrained case is that now the gradient will be zero at the solution only with respect to the inactive variable. The other variable are, the other gradient components are need to satisfy simply a sign constraint. Then, a possible explanation of the fact that the rule works also in this case in a similar way to the unconstrained case is that if we denote by this notation jk-1 the active set, the set of indexes that correspond to the active variable which already have the gradient with the correct sign, and with ik-1 the complementary set, then a possible idea to explain this behavior is that the steplength rule probably accelerates the reduction to zero of the gradient components that are corresponding to the variable that are inactive. That is the gradient components that will be zero at the solution. To verify this suggestion, it is important to check how the Barzilai borrowing rule can be written in this constrained case. To do this, it is important to observe that the difference of two consecutive iterations, now will be zero for the components with index within the active set, within the set of active variable. This means that the first rule is written in terms of only the inactive components of the vector. Then the first rule in the constrained case can work as in the unconstrained case, but with respect to the so-called reduced Hessian matrix. That is the Hessian matrix obtained by the original Hessian matrix by considering only the columns and the row corresponding to inactive variable. This conclusion is not true for the second rule, since the second rule includes also a term that depends on the active variable. And due to this term, it is impossible to prove for the second rule the spectral property that I recalled for the first rule. Okay? Then there is a difference in the behavior of the first and the second rule when you use this steplength rule in the constrained case. The first rule seems to preserve some kind of spectral property. The second rule is not able to do this. Okay? And when you try to solve some test problem with the two different rules, you find that the first rule is able to sweep within the spectrum of the reduced Hessian matrix, while the second rule is not able to perform an effective sweeping within the spectrum of the reduced Hessian matrix. Then the possible suggestion is try to modify this second rule when you are in the constrained case. The modification consists in deleting the term that depend on the active variable. And to use a BB2 rule modified BB2 rule, in which only the term corresponding to the inactive variable are preserved. If you do this, then you recover all the property that we know in the unconstrained case. Okay? Then we have that also the second rule is able to sweep within the spectrum of the inverse of the reduced SS matrix. And the second rule, at each iteration, provides values that are smaller than the first rule. Then, also in the alternated rule that we have observed very efficient in the unconstrained case, we suggest to exploit this modified rule, BB2 rule, instead of the standard BB2 rule. And we find convenient to work also in this constrained case with alternated rule instead of the use of a single Barzilai borrowing rule. Okay. We verified this behavior on many test problems, randomly generated, first in the case of box constraint problem, quadratic problem, and then also in the case of general box constraint problem. But the conclusion is exactly the one that we have obtained in the unconstrained case, if we use this new modified BB2 rule. This performance profile suggests that the modified rule always outperforms the standard BB rule. When I use the modified rule within the alternated scheme, I perform better than the standard alternation of the classical Barzilai borrowing rule. And usually, the new alternated scheme outperform the use of a single BB2 rules. Okay, similar analysis has been performed also in general constrained, box constrained problem, and the conclusion is the same. That is, as you can observe by this performance profile, it seems convenient to exploit alternated Barzilai borrowing rule. This consideration is important, in my opinion, since in the last year, many interesting applications have been solved by gradient projection scheme with Barzilai borrowing rule, both in machine learning and in imaging. Then, to know the possibility to further improve this, the behavior of this gradient projection scheme with this step length that take into account the spectral property of the rule can be useful for further improve the behavior of this scheme. Concerning application in imaging problem, we need to discuss another important topic, in my opinion. That is the use of the scaling. That is, gradient projection scheme in many imaging reconstruction problems can provide very better performance if it exploits also the scaling matrix in defining the direction. In practice, I can proceed with the last part of the talk concerning the scaling gradient matrix method. In practice, I said in imaging, it could be interesting and useful to exploit the gradient projection scheme in this form. That is, by using not only the gradient direction, but the scaled gradient direction. Here, the matrix D is a symmetric positive definite matrix. And this symmetric positive matrix needs to be used not only in scaling the gradient, but also in defining the projection in a variable metric framework. Of course, now in the scheme you have two classes of parameters. The classical step length parameter alpha k, but also the parameter concerning the use of the scaling matrix. And then we need to discuss both the choice of the scaling matrix and the way in which the step length parameter that I have discussed previously in this spatial setting in which there is also the scaling matrix. And then I cannot fix the step length simply try to exploiting the spectral property, but I need to take into account also the presence of the scaling matrix. From a theoretical point of view, these two parameters, the step length and the scaling matrix, needs not to satisfy restrictive condition. Then I can work as these two parameters are free parameters that I can try to fix in order to improve the performance of the methods. Okay? In practice, for the convergence results, we simply need that the scaling matrix has eigenvalue bounded below and above by not restrictive condition. This. Okay, then possible choice for the scaling matrix. Of course, we are thinking to simple choice, for example, diagonal scaling matrix, and inexpensive choice, that is choice of the scaling matrix depending on only first order condition, first order information, not second order information. And a possible suggestion comes from some kind of interpretation that I try to summarize now. The first is this one. Suppose to have a non-negative constrained optimization problem, that is a classical situation in imaging, and look at the KKT condition for this problem. In particular, look at the system of nonlinear equations given by the first KKT condition. Now, if you suppose to take a splitting of the gradient as the sum of its positive and negative part, and exploit this splitting within the system of nonlinear equation, you find that the KKT condition is a fixed point problem. And when you try to exploit a fixed point iteration for solving this problem, you find exactly an iterative scheme that is a scaled gradient method with a spatial scaling, with a very spatial scaling. Diagonal scaling with entries equal to the ratio component-wise of the current iteration and of over the positive part of the splitting of the gradient. This is completely inexpensive since involve a quantity that are already available in the iteration. And if I exploit this kind of scaling within a general gradient projection approach, in some sense I mimic a fixed point iteration on the KKT systems. This is the first interpretation of this scaling. But we obtain the same conclusion even if we try to give another interpretation of this scaling based on a majorization minimization approach. In fact, suppose to minimize this general discrepancy function. This is a very general way to describe discrepancy functions that include the classical discrepancy function like the least square discrepancy function or the Kullback-Leibler discrepancy function as spatial cases. Given this discrepancy function, it is possible to define a surrogate function up to an additive constant by exploiting just the splitting of the gradient of the discrepancy function in its positive and negative part. This is the expression of the surrogate function. Then, given the surrogate function and taking into account the spatial form of the gradient of the surrogate function, if I try to exploit a majorization minimization approach to solving the minimization problem, then I find this spatial multiplicative algorithm. When I write this multiplicative algorithm in the spatial case of the least square divergence or Kullback-Leibler divergence, then I find this multiplicative algorithm that is exactly the scaled gradient step previously described. And then, also in this case, I can try to interpret this scaling as a possibility to mimic a step of majorization minimization method, that is a descent step for my objective function. This is another interpretation of this kind of scaling. For completing this discussion, I remember that this kind of scaling are the basis of a very popular algorithm in imaging. For example, the ISRA algorithm for minimizing this least square divergence is just a scaled gradient method that exploits this kind of scaling. The Richardson-Lucy or expectation maximization algorithm for minimizing the Kullback-Leibler divergence is just a scaled gradient method that exploits this kind of scaling. Then if I try to exploit in imaging this kind of scaling, I'm working with a scaling strategy already exploited by other algorithms. Of course, within my general scaled gradient projection scheme, I need to respect the theoretical request that the entries of the diagonal matrix are bounded below and above by positive constants. Then I need to bound the entries of the scaling in this way. Okay, I have no time to discuss other kind of scaling. I prefer to finish this discussion by observing how the step length need to be modified in case of scaled gradient algorithm. Also in this case, I try to exploit some consideration in a simple case, the quadratic case. And in this case, the consideration is this. If I try to perform a scaled step on my original problem, this one, then I observe that this is equivalent to perform a non-scaled step on a preconditioned problem. Okay? In the sense that the new iteration that I find with the scaled step in the original problem is related to the new iteration that I find with the non-scaled step on the preconditioned problem by this formula. Okay? Then the idea is that in case of scaled gradient step, the step length can be fixed to the value provided by the non-scaled step on the preconditioned problem. Then the quantity that I need to change are the difference of the iteration and the difference of the gradient that now are written in this way. By performing this choice, we have a scaled version of the Barzilai-Borwein rule that take into account the presence of the scaling matrix. This for the BB1 rule and this for the BB2 rule. Okay? And also in this case, it is interesting to provide another interpretation of this choice. We may observe that this choice are obtained also by asking the original quasi-Newton property, the original second condition, but not in the Euclidean norm, but in the norm defined by the scaling matrix. Okay? Then we can give different interpretation to this rule. Okay. If we use this step length in case of box constraint problem, remember to use the modified rule. Okay. And then we can try to complete my presentation with a simple example in imaging in order to verify if all the considerations presented in the talk also in these practical cases related to the image area. I consider an image reconstruction problem in computed tomography. In this case, the optimization problem is this one, in which I have the least square discrepancy function and a smoothed total variation term as a regularization terms, and simply non-negative constraints. In this case, the diagonal scaling is obtained by generalizing my consideration also to the regularized. That is, I consider the positive part not only of the discrepancy of the gradient of the discrepancy function, but also the positive part of the gradient of the regularizer. The test problem is a phantom. Is based on the well-known phantom. Here we have the size of the in terms of voxel of our problem. This is the number of columns of the projection matrix, while the number of rows of the projection matrix is given by the number of angles of projection and by the size of the detector. The test problems are performed with a non-optimized code, a simple MATLAB code, and is aimed to verify if both in the unscaled and scaled settings, all the improved steplengths that I have discussed can be of some kind of utility. Finally, I consider also a comparison with a standard algorithm like Vista or its scaled version. First consideration about only the gradient projection scheme. We can observe that a comparison among the different rules that I can exploit, the standard rule BB1 and BB2, the modified BB2 and the alternated rule, provide also in these practical cases the same conclusion observed in the talk. That is, usually it is convenient to exploit alternated Barzilai-Borwin rule by including the new rule designed for the constrained problem. This is true also in the scaled settings. Okay? Also in this case, the alternative rule seems to work much better. In order to discuss the behavior of the scaling approaches, it is interesting to look at the reconstruction error provided by few iterations, provided by after few seconds. That is, in my opinion, the important consideration, since in many real-life applications we have no time to wait for hundreds and hundreds of iterations. We need to provide some reconstruction after a few seconds and then evaluate its quality. If I look at the relative reconstruction error, we see that the scaled version, after a few seconds, can provide a much better quality of the reconstruction with respect to the non-scaled version. Then this is another confirms that the scaling is useful in accelerating the process in the first iteration. And this is true also for the Vista approach. That is, standard Vista have this behavior, while the scaled version of this algorithm that I recall in this slide can provide much better reconstruction in the first iteration. Okay? In this case, the scaling metric works on the forward step and also in the line search that we perform to adapt the step length alpha k in Vista. Okay, I hope that something can be observed also in the reconstruction. Here I have reported the reconstruction after 5 seconds and 20 seconds. That is after 20 iterations in this case and 8 iterations in this case. And we can observe that the scaled version seems clearly better, especially after 20 seconds the reconstruction seems very, very good. I have reported also the comparison with the true image, and after 20 seconds the reconstruction seems satisfactory. Okay. I can conclude with some consideration. I have presented some idea concerning the spectral property of the step length in the unconstrained case. This consideration is useful not only to understand the behavior of the step length in the unconstrained case, but it is useful also to design new rule for the constrained case. These topics is not widely investigated in literature, then I suppose that can be useful to improve standard gradient projection scheme. Furthermore, I recall the importance to use the scaling matrix in the gradient projection application to image reconstruction problem. And in that case, it is of course important to adapt the step length rule not only to exploit spectral property, but also to exploit the presence of the scaling matrix. Work in progress are concerning the generalization of this idea to other interesting feasible reasons. For example, this one is a feasible reason given by box constraint and a single linear equality constraint. That is a feasible reason that appear frequently in application. And then preliminary results suggest that also in this case, even if the analysis is complicated by this term, but preliminary results confirm that it is important also in these settings to exploit spectral property of the step length. Furthermore, we are working on possible extension of some of this idea to the stochastic framework, and also to provide efficient implementation of the software for computed tomography that I described. Okay, I think that this is all. Thank you for your attention.
Okay. So we have time for questions to Luca. So,
I was wondering what prevents you from applying this to explicit, implicit algorithms, typically for backward, for instance?
Sorry, so can you repeat?
Can you apply this with projected gradient descent or with for backward, typically? And the same analysis holds true, right?
For all backward algorithm, the step length need to satisfy some other condition. It's not so free as in the gradient projection scheme. For example, in case of the fixed approach, this need to satisfy some kind of descent condition. While in the general gradient projection scheme, I'm completely free to choose this step length parameter, since this line search technique works on the descent direction, not on the choice of the step length. I don't know if this is the...
So it's not possible to replace the projection by a proximal operator?
Yeah, by any function. Beside the integral function of omega, you can just take...
Okay, okay. In this sense, it's correct, okay.
It's possible?
Yeah, in this sense, it's possible, okay.
So in practice it works, or the theory also works for a proximal operator instead of a projection?
I think it is possible to extend since the proximal and the projection works in a very similar way.
Computing the omega in the metric dk minus 1 is going to be as difficult as the original problem is omega is not separable, right?
Yeah, of course. My first assumption is because the feasible reason is simple. If the feasible reason is not simple, then all the projections are complicated. And also if the scaling matrix is not diagonal, you have the complication if in performing the projection, of course. Okay.
So is it possible to consider some special shapes for the scaling matrix that are non-diagonal? So I think in general it works, for instance, if you have a low rank matrix or something like this, is it some diagonal plus low rank or something like this?
The importance is that this does not introduce too much expensive cost in the iteration, of course. But if you are able to exploit different matrices that are cheap within the iteration, it is possible to explain.
Okay, so maybe Okay, Pierre?
Yeah, maybe one question, you also have the alternative methods would be like LBFGS methods, which can also be extended to box constraints. So how would they compare? How would the...
There are interesting comparisons between BFGS and some kind of advanced step length selection strategy. And there are very similar comparisons, very similar results. In particular, I can recall one of the last paper of Roger Fletcher in which he generalized the Barzilai borrowing rule by introducing memory on the gradient. That is not the use of the last gradient, but the last M gradient. Then, in this way, we have a very, very similar behavior of BFGS, and sometimes also better than BFGS. In fact, another extension of this analysis is just to try to perform the spectral analysis also on the limited memory strategies, like the one suggested by Fletcher some years ago.
And in terms of guarantees? Convergence guarantees and so on?
From a theoretical point of view, we have the standard result of linear convergence. All these strategies need to be evaluated in practical performance, but from the theoretical framework is the same for all of this approach. I'm not able to give you a proof in which, with this rule, perform better than the standard scheme. But within this general framework, you can try to improve the performance. For example, in the first iteration, this is a consideration that is interesting in my opinion. Okay.
Okay, so if there's no questions, let's thank Luca for his talk. Now there is a half hour.